So I want to remind everyone we have the exam on Wednesday. Let's see. Dates. Yeah. Exam 3 is Wednesday, and that'll be our last exam until the final exam. And the reason for that is because there'll be no class next week because I'll be away at a conference, and don't know anyone that could sub in for me. And then the week after that is Thanksgiving week, and we'll have class on Monday, but not Wednesday. So we'll be a little sparse coming up here for the next 2 weeks. Today I planned on mostly just reviewing for the exam, and I might get back into chapter 5 a little bit towards the end. But the problem is I'm afraid that I don't want to get too far into that because I'm afraid that since it'll be a while before we have class again, I'm afraid that you might forget. So let's see, where should we start? We can start with quiz. I think I went over quiz 6 last time, right? So quiz 7 was the quiz from last week. It was due by Friday. Make this zoom in. There we go. Okay. Give the value of signal A in the first 3 clock cycles. So this is a snippet of System Verilog. It doesn't have the module line or the end module. This is just, like a part of a module. We declare a local signal called A that's 3 bits. There's an initial block that initializes that to 101. And then there's an always flip-flop triggered on the rising edge of the clock that has 2 assignments for A. The tricky part here is that one of the assignments is blocking and one of them is non-blocking. So blocking assignments are mainly designed for when you want to take an expression and split it into multiple statements, as opposed to assigning something on one long line of code. So in this case, it's kind of like saying, I want to assign A, I want to shift A by 1 bit to the left, and then because this is a blocking assignment, I want to substitute the value that I calculated for A here into the following statement, which also uses A, and then it XORs it with 111. Okay? Yes?
If the order of those 2 assignments were different within the begin and end statement, would that matter?
Yeah, that's a good question. I'm going to test that today. We'll give that a shot and see if it makes a difference. In this case, it's pretty obvious based on the order they're in, with this being a blocking, that we want to use the updated value of A here, right? But if they were reversed, it's unclear. We'll give it a shot. But for this problem, we know that A is going to be start out as 101, and then in the next cycle, when this always activates, we're going to shift A 1 bit to the left, which is going to give us a 010 based on the result of that first. Because you're shifting to the left, meaning that the leftmost bit gets knocked out, and we shift in a 0 on the right-hand side. So it gives us 101. And then whenever you XOR with 1s, it inverts. That's XORing with 1 is just another way of saying I want to complement each bit. So that's going to transform it back to 101. Okay, so the final value of A after the first cycle will be 101, right? You'll never actually see this value because this happens entirely inside this sequence. right? You'll never actually see that. You'll never see A become 0, 1, 0 because that's part of it's part of the evaluation of the final assignment. You guys with me? And so you can see now we're back to 1, 0, 1. So of course every cycle it's just going to stay 1, 0, 1. It's never going to change. It's going to keep getting reassigned because if you go to 1, 0, 1, you shift and you invert, you arrive back at 1, 0, 1. Yes? Oh yeah, that's an XOR. So XOR, if you take 1, 1, 1, right, and you XOR it, XOR is it's a modulo 2 differencing operation. If you XOR with a 1, if you take a value and XOR with 1, it flips it. If you XOR with 0, it does nothing, right? So 1, is that right? Or maybe not? Oh yeah, that's right. Yep. So 1 XOR 1 is 1. 0 XOR 1 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. All right, does that make sense? So this was kind of, the point of this problem was to hopefully shed some light on this blocking versus non-blocking behavior was the idea. So let's give this a shot.
Blocking is the fixed value and non-blocking is the previous.
The way you think of it, sometimes the terminology still screws me up, but non-blocking is this little arrow looking thing, less than equal sign, right? And non-blocking is what you're supposed to always use in an always underscore flip-flop, right? So normally I would have only used this because this is a flip-flop. It's a sequential always statement. It's an edge-triggered always statement, some clocked or registered, or there's many different names for it, but it's a edge-sensitive always statement. So normally you would always use the non-blocking by convention. You don't have to though, so this would not generate an error, but the convention is to use this. You can mix them, which is what I did here, and by mixing them, it reinforces what it really means to be blocking versus non-blocking. So blocking means that it behaves as if you were writing this in Java, right? So you make the assignment and it takes effect in the next line of code. A non-blocking is you set the non-blocking and it's kind of has a delayed effect. It doesn't take effect until you're done evaluating everything in the always block. And in fact, in reality, it's actually more complicated. It actually doesn't set it until you've evaluated every statement in your whole design that was triggered by that edge, by that event, right? The book doesn't get into that level of detail though with it, but I've learned that through experience. Because it turns out in the past version of this class, when we actually did more coding, that was a very common bug that people would hit was this, if you didn't use the right assignment statement. It comes up quite a bit. And sometimes its effects go beyond, they cross multiple always statements, sometimes in different files. So you have to be careful with that. But let's give that a shot. Let's try an example of that. Connect to a machine. User local third-party CAD setup files altera.bash. Examples. Yeah, it's cool. By the way, just want to remind you too, I put a tutorial on the website on how to do this stuff if you're interested in practicing. Okay, Vim example 1.sv. Okay, module test example 1. Should name it the same thing. End module. Logic 2 down to 0. A. Always. Oh, we need a clock too. Logic clock. So I point out, I did not I didn't declare the clock in here because this is just a snippet, right? But in order to actually run this, I need a clock. I didn't have the module line in there either. Okay, always underscore flip-flop at pause edge clock, begin, and I need a begin and an end there because I have multiple lines. Hopefully I had that in here too. Yeah, I did. Good. Begin and end. Okay, so then A equals A shifted by 1. A equals A XOR 3 apostrophe B 111. Right, and that's it. Okay, save, compile it, and simulate it. Oh. And of course, this is going to be super slow. Come on, Model Sim. This is the problem with Model Sim. I wish I'd have thought to have Ryan install Icarus on these machines. Model Sim's very powerful, but it's slow. Actually, I might have to, hold on, I might have to reconnect. Sorry. This MOBA Xterm program gives me an X server on my Windows machine, but it's a little flaky. Source user local third-party CAD set of files altera.bash examples vsim example 1 space no vopt. There it is. Okay. Oh, it crashed. All right. Can I try again? There it is. Okay. All right, so Model Sim comes up and it immediately starts the simulation. I can already see A and clock. The first thing I have to do is I want to add these to my wave, and then I have to set up clock. I don't have a test bench for this, so I need to have Model Sim. I guess I have to do it in the wave, yeah, in the wave window. Ah, dang it, crashed again. Sorry. I'll give this one more shot. Normally you would have a test bench with this that would set the clock up and also set a value. I guess I don't need to set an initial. A is already initialized, so I shouldn't have to set that. So this thing should run just with a clock. I just give it a clock heartbeat and it should go by itself. But I don't have a test bench. In fact, you know what? I could add that pretty easily. Let me give this one more shot here and see if. Okay, so I'm going to go right click here and go to clock and hit OK. This will just have the clock go and okay, well there we go. There's the 5. That's 5, so that worked out. I'm not sure what happened at the beginning here though. Let's see, let's zoom in here. I'm afraid to maximize the, here we go. Okay. Well, we got the right answer, but there was some, there seemed to be some confusion at the beginning there. Look at that. So the X is an undefined. So the first rising edge, it actually was undefined 0, 1. And then on the second rising edge, it stabilized to become 1, 0, 1, right? So it took 2 cycles. It got to that answer. It took 2 cycles. I'm not sure why though. It's very, very strange. So let's try it the other way. Let's flip those statements around. Oh. So now we're doing it in reverse. So let's see what this does. Let's give it a shot. Go to library. Oh, actually, I just had to. I don't have to. I already recompiled. I just have to restart it, and got to set up the clock again. This is another reason why you want to have a test bench. See, every time I restart this, I have to go in here and set up this clock. Oh, look at that. Well, now it's totally dead. So I killed it. That's interesting. Let's try something else. Let's reset it. Let's have a reset signal. Yeah, probably what happened here was, oh, I forgot the initial here, didn't I? Oh, yeah, I did. Oh, why didn't, you guys must not be paying attention. Initial A, 3, that would explain what's going on. 3, what did I initialize it to? 101? It's kind of interesting, though, that it's weird that it got to 101 even without the initial. It just took 2 cycles to reach that. That's kind of crazy. You know what it must have been? It must have been the shift. So A started out as undefined. But when I did the shift operation, every time you do a left shift, it shifts in as 0. That 0 is guaranteed to be a 0. So the reason it took 2 cycles was because it took 2 cycles for me to shift in enough zeros for it to actually take on a value. So essentially I initialized it by doing a shift left and getting the initial data by shifting in zeros. So that's why there was that delay. That's interesting.
If you don't initialize it, it's 0.
If you don't initialize it, it's undefined. That's what those red lines were on there. In fact, now it's
so it goes to 0.
It crashed again. But it just goes. It's red on Model Sim. Most waveform viewers, I think, will show it as red, meaning that I don't know what it is. It's a signal that I never set. I never forced it to be something in the simulator, and if you don't initialize it, it just comes up as in real hardware it would be random, just like in C if you don't if you have like a global variable. Or some dynamically allocated variable that you don't initialize is just random, right? But Model Sim it doesn't want to, it marks that as being undefined instead, because if it just randomized it, it would be difficult to track down uninitialized variables. Does that make sense? Okay, let me give this one more shot. I don't know why it's crashing. It must be interfering with my recording software here. I'll recompile this and, there we go. Variable A is driven in always FF block, may not be driven by other processes. Oh, that's interesting. I didn't like that. How about this? Let's delete that and put it back to the original order. So initial A, okay, and vlog. Oh, it still doesn't like it. Okay. Well, that must be a symptom of the, what if I just say always instead of always FF? There we go. Okay, so that's interesting. So if this were regular Verilog, I would just say always at pos edge clock. System Verilog introduced the always _FF, whose sole purpose is just to cause errors when you go to compile it if you do something strange. Well, apparently it considers this strange for whatever reason. And so by taking out the _FF, I disabled that additional level of error checking. But let's give this one more shot. I want to see if I can make sure that I get the same answer I got before. So yeah, compiled, right? Okay, right. vsim. Yeah, this is actually the first semester I've used System Verilog. I normally just use plain vanilla Verilog. All right, so let's go put these in our wave again. Drive our clock. And run. And look at that, it still takes a little while to stabilize. So I still get 5, but yeah, the initial doesn't work. Oh, that's interesting. It could be because I mixed those two signals together. If I expand that, you can see that bit 0 is 1 from the very beginning. And that makes sense because on the first rising edge, so if you look over here, the clock actually, there's a little bit of a rising edge. The first edge of the clock is a rising edge right at the beginning. So that's enough to trigger that always statement. And so bit 0 starts out as 1. And that makes sense because I had a non-blocking assignment. Sorry, I had a blocking assignment where I shifted in a 0 because I did a shift. And then I immediately negated it with that XOR. So that first 1 is from the shifted in 0 negated, or complemented. Then in this cycle, bit 1 falls because I did another shift. I'm kind of surprised though that we didn't get I didn't get a 1 there though, because after the first cycle, let's see. So if I started out with XX1, then the first line of the first line there would have so I would have did the shift first. So that would have given me this. Oh, right, and then I would have negated it, which would have given me 0, 1. Okay, that makes sense. Yeah, good. Everyone see that? Right? So first cycle, I've got this. Second cycle, I get this because I would have shifted, negated. And then the third cycle, I would have had X, 0, 1. I would have done the shift, so I would have said that would have been a 0, 1, 0, and then I would have negated that, which is 1, 0, 1, and that would have been my final value for that cycle. Everyone with me? I don't know why the initial did not initialize it though. It could have been because of the type of assignment I used for that. So if I switch that one to a blocking. All right, so I recompiled. Restart, and then run 200. Did it restart? Yeah, there we go. Yeah. Okay, so, oh, sorry, I need a clock. Well, in this case, check it out. I don't even have the clock going. The clock is undefined, but yet A was initialized to 5, as it should have been. So now if I get the clock moving here, let's see what happens. There's the clock, and of course it doesn't change. What happens though, just out of curiosity, if I restart this and I set the clock from the beginning, I wonder if there's something strange that's happening at the beginning. Set the clock up, hit OK. Now I run it. Oh, and of course I switched it too fast. All right, well anyway. Any questions? I think I've beaten that one to death. Okay. Next question. What is the problem with this code? This one is an always underscore com. This one definitely wouldn't compile because I've got this loop back, right? This is essentially a circuit that would have to have, well, this would end up being an oscillator, actually. I was about to say it would have memory, but actually it wouldn't even be stable because you would be trying to add, you'd be trying to add 1 to a value without any kind of delay or register in there, flip-flop, right, to synchronize it on the clock. So it would just be essentially a cross-coupled, an unstable cross-coupled circuit. Everyone with me? Right? So to solve this problem, if I were to ask you how would you fix this, you could just say always underscore flip-flop pause edge clock, and that would be fine. Then it would just be a counter. It would just count every cycle.
Say post edge?
Yes. Or neg edge, either one. As long as there's an edge, yeah. As long as it's edge triggered. This wouldn't work as a latch, by the way, because if this were a latch and it was level sensitive, not edge sensitive, you'd have the same problem. Because when the clock was high, the latch would be open and you'd still have an unstable circuit. So it has to be, it's very important that this be edge triggered. Any other? Yeah. Oh, and this was a little bit, I had a few people ask me about this. The always statement shouldn't have a begin and end. It doesn't need a begin and end because there's only one statement in there. But the fact that it has a begin and end isn't a problem, right? Okay, next. Okay, there's a test bench. What function does some module perform? So the test bench instantiates a module called some module. It calls it dot, and it wires A, B, and C. Oh, that should be a comma, actually. Yeah, I just noticed that. Sorry, that there's a little typo. That should be A, comma, B, comma, C.
So it wires those, and then it says it starts with A and B with 1 bit, and then if C is not, or if C is not bit 1, it displays an error. So that means it's 1, 1, 0 there. The next one is 0, 1, 1. Then 0, 0, 1, finally 1, 1, 0.
That's right. So I lost you there. A is 1, 1. Sorry, starts out as 1, 1, 0, right?
Yes.
A is 1, B is 1. I expect C to be 0. Oh, sorry, I expect C to be 1.
It can't be 1.
Well, if it's not 1, see, this is the thing about it. This is how test benches work. You have an expected output here, right? The expectation is that C is 1. But if it's not 1, then I'm going to print this error message, meaning that that's a problem, right? So the expectation is that C is a 1. Now, if I change A to 0, B will stay 1 because I didn't specify B here. I just said A. So B will stay whatever it was. And I'm expecting C to be 0. And then I change B to 0. A will stay 0, right? So now I'm expecting C should be 0, right? And finally, I change A to 1. B stays 0. You guys see that? This is now I'm on this line of code. I change A to 1, and B ought to be a 0. Make sense? So that's a AND gate, right? So I can tell just by reading the test bench that this thing is whatever this is creating an AND gate, even though I don't have the description of that module. Any questions about that?
How can you tell it's an AND gate?
Oh, this is a very simplistic case. I'm not trying to say that you can always tell what something does by reading the test bench, But in this case, the test bench is going through every possible input combination, and there's an expected output, right? So based on that, I can reconstruct the truth table. And based on the truth table, I know it's an AND gate because the output is 1 only when the inputs are both 1, right?
So you're doing C as the output.
C is the output, right, yeah. Yeah, and I know that just from the context because I'm setting A and B and I'm reading C, right? So I know C must be, these must be the inputs and that must be the output just because of the way that I'm referring to them in the test bench, right? Otherwise, you wouldn't know what's A, B, and C mean. Could mean anything, right? But based on the context, I know that A and B are the inputs, C must be the output. Make sure you know how to do this. There is a problem on the test where you have to build a little test bench just like this. This is a self-checking test bench in the sense that it pretty much does all the work for you. You would just simulate this, and if you don't get any, as long as you wrote the test bench right, if you simulate this and you don't get any errors, then you can be reasonably confident your design under test is working the way it should be, right? Yes?
When it says when A is 0, C will be 0, is that just assuming B will be 0 as well?
Right, that's the other thing too, and I did that deliberately. I didn't change, like in this, I initialized A and B to 1 and 1. But when I get to the next test case here, I changed A but not B. I did that because you should know that B wouldn't change from its previous value if you did that. Okay. And by the way, I didn't point this out, but this pound 10 is also very important. This means to weight 10 units, 10 time units, right? You have to put a weight in between when you set the inputs and you check the corresponding output. Now, how much weight do you have to put in? It could be 1. It doesn't matter what it is. You have to wait for some amount of time, right? I don't know why I put 10. I guess I'm just used to using 10. You guys with me?
Yes.
So on the exam, we write this.
Yes, yeah. Make sure you just understand the basic form. So a test bench it's comprised of you have to instantiate your design under test, right? So you got to put this in. You have a design that you're testing, so you have to put it in as structural Verilog, right? So I put it in here. I just create it kind of like creating a Java object. And then there's an initial block, and the initial block runs through each test case. Each test case is going to be setting the inputs, waiting, and then an if statement to check for an error, right? Checking the output as compared to what you expect the output to be, right? So C is the actual output, 1 is my expected output, right? So this thing is checking itself. It's doing all the work. It's setting the inputs and it's checking the outputs. You don't have to check the outputs, but if you don't, then you're going to have to do it yourself manually by reading the waveform, right? Likewise, the book presents a way to put each one of these test cases into a file called a test vector file. That's just an added convenience that cuts down on the amount of code. You see this big block of code is pretty unwieldy. It would be better if we could just essentially loop through test cases that are specified in a separate file. I'm not going to have you do that on the test because that's kind of complicated. If we were actually writing this in class, like in a lab, then I would have you do the test bench like that. But in this case, it's easier just to type it out, like just have the test cases built in. Yes?
Is there any reason why you only change one at a time?
No, you could change them all if you wanted to. If you wanted to like copy and paste these 2 lines of code over and over again, that would be fine too. I just did it to try to trip you up a little bit. I wanted to point out that in a test bench, if you don't change a signal, it stays whatever it was, right? Which is what happens here. I change A, I don't change B, so B stays the same as it was, right?
Okay, and if you did like A changes 0, B changes 0, if you do that, then both of them.
Oh yeah, you could do them both, sure. Yep. Yeah, it's no problem. Yes?
So you would want us to design like an AND gate, for example.
Yes, and yep.
Or an OR gate or something.
Sure, and then write a test bench for it. Yep, absolutely. Yes, just something simple like this. Okay. Next. what are the first three values of A? So this is just bit twiddling. So A starts out as 10101, 10101, and this one will change A every cycle to some function of whatever it currently is. In this case, it takes the least significant bit and puts that first. So that, remember the bit 0 is going to be the right bit, right? So I'm going to put that first. That's now the left bit. And then I take bit 1, which is the second to rightmost bit, and reproduce it 2 times. So that 0 gets copied twice, 0, 0. And then I take bit 3, which is the second to leftmost, second to the left, and I complement it. So this is bit 3. This is bit 0, 1, 2, 3, 4, right? So bit 3 is right there, it's that 0, so I complement that, that becomes 1. And then the final bit is bit 2 XOR bit 4. So bit 2 is 1, bit 4 is 1, 1 XOR 1 is 0. So then the next cycle I just do the same thing. So start out with bit 0, which is a 0. Then 2 bit 1s, which is 1, 1. Whoops, 1, 1. Then negated bit 3. Bit 3 in this case is a 0, so that's a 1. No, sorry. Oh, yeah, that's right. Yep. And then 2 XOR 4, so 2 XOR 4, so that's a 1. That would be a 0 XOR 1. 1. Right? So those are the first 3 values. Hopefully, let's see, did that work out? Is it B? No, it's A. 10101. Oh. Yeah, it scrambles these answers every time you open the questions. So 10101, 10010, 0, 1111. Yep, C. Okay, any questions about that?
I have a question.
Yes.
For question number 2.
Okay, let me back up here. This page. Okay.
So I thought that an always statement would also always need a sensitivity test.
An always statement does, you're right, but not an always comp. Yeah, you're correct. If it was a plain always statement, you'd have to put a sensitivity list. That's a great question. In regular Verilog, you would have to have a sensitivity list. So you'd have to say always at, and then you'd put star. This is the way you'd make combinational logic. Star means any signal changes that's treated like an input in here, I want you to update it. But this is equivalent in system Verilog is saying always underscore com, right? The advantage of using always com is that, like I was saying earlier, it puts additional error checking in, right? So if you did this, if you did always at star and you had exactly this code except use always at star, no error. It would be fine. It would compile. It just would act all goofy. But if you put always com with this, it'll give you an error because it'll say that's not valid. It's not valid combinational logic. By putting this idiom in, this is a new idiom they put in. It's a way for the programmer to convey to the compiler what you're trying to do. And if whatever you're doing doesn't fit the pattern, the template of what you're saying it does, it'll give you an error, right? So it's just an error check. I don't know if you noticed, I got that error in that example I did. It wouldn't let me do always underscore flip-flop. I didn't think it was proper Verilog for always underscore flip-flop. Yes?
Question 4, what would be A2 clear A4?
That's an XOR. That takes two of the bits from the previous state and XORs them together. By the way, this what's happening here? What does this circuit do? This is a random number generator. Kind of cool. I mean, if you let this thing go, it'll just keep giving you these random numbers. It's kind of neat. There's a lot of circuits that actually do this. The problem, this is probably not a good random number generator because I don't know, it may have a very short period. Period being, you know, how long it takes for it to repeat the pattern. So it probably isn't a very good random number generator, but that's what it's doing.
So for the second cycle, for that A2 period A4, that would be 1.
2 and 4. For the second, yes, because 2 is 1 and 4 is 0, right? 1, sorry, you're right. Yeah, 4 is the leftmost one, right? Yeah. Yeah. B0, because it's 1 XOR 1 is 0. Yes? Got it? Okay.
And how do we know how many times do we have to go through it?
Oh, because I said 3 times. I said first 3 values. Yeah, I'm kind of interested I wonder how long how long that would run before it would start, repeating the same sequence again. These are called, this doesn't exactly fit the form, but in general, these are called linear feedback shift registers. It's doing a shift operation, and it's doing XORs. So that's what creates the random sequence of values. So like, if you wanted to generate an encryption key, you would let that thing run for some amount of time and then stop it, and whatever it lands on, you can use that as your, random seed or key or whatever. Yes?
Would that be better if you had the actual size and the time frame?
If you knew the design and the time it ran for, yeah. Yeah, but if you ever use one of those programs that it'll tell you to move your mouse around or something, and it'll give you the key that way. Okay, let me run through the quizzes now. These shouldn't take too long. Here's actually this is another random number generator. This one is actually called random number. So this is a very similar problem. This one has the full module though. Has a clock, a reset, has a load input. It has a seed input. This is the starting value. So instead of using an initial statement as I did in the last example, this actually takes an input, and it has an 8-bit output called value. And then it has always at pause edge clock. Notice I don't have underscore FF here because this is regular Verilog, but you could also put underscore FF here if you want to. It says if reset, then I'm going to take the value and set it to 0. If reset is false, then I'll get to the else if load is 1. So if reset is 0 and load is 1, then I'll take whatever the seed is and I'll put that into my value. Else, the value is, and then more bit twiddling. In this case, I take value 5 XOR value 2, set that as the leftmost bit, and then I take the rest of the bits from val except for the rightmost bit. So in this case, I'm doing a right shift, but I'm shifting in val 5 XOR val 2. So this is kind of a variation on that. On that example I gave earlier from the quiz. How many input signals are specified? 1, 2, 3, 4. How many output signals? Just the 1. What is the purpose of the reg keyword? This does not apply to us. So in Verilog, there was a type called reg, which is how you had to declare any signal that was set by an always. And if it was set by an assign statement or from another module, then you would declare it as a wire. It made no sense, and it was ridiculous because it was so hard to get that right. So System Verilog fixed that by just changing everything to logic type, right? So you guys don't have to worry about reg versus wire. You can just declare everything as a logic in System Verilog. It's nice. Only took them 30 some years to fix that. Fill in the last column in the table. This is a table that would track the value of that random number generator for the first 5 cycles. So cycle 0, I'm going to reset it. So I'm giving it a seed, but I'm resetting it. So the value there would be well, actually, was that a synchronous reset? Yes, that was a synchronous reset, right? I didn't have pause edge reset in the sensitivity list. So as a result, I'm resetting it in cycle 0, but that reset would not take effect until cycle 1. Meaning that when I'm filling this table in, the first value is an undefined. I don't know what it is. In cycle 1, it will be a 0 because I had a synchronous reset. And at that same time, I'm loading that seed in. So that seed value will become the value in cycle 2. You guys with me? So what am I saying? I'm basically just saying everything gets delayed by 1 cycle because of that synchronous. And then in cycle 3 and 4, I'll have to apply this shifting operation. Everyone with me? So cycle 1, I look at cycle and val. Cycle 0, val is, I don't know what it is. Whatever it was. I don't know what it was because I don't have an initial block. Cycle 1, val would be a 0. How many bits is it again? 8, right? Yeah, 8 apostrophe B0. Cycle 1, it'll be the seed. Whatever I put in is the seed. So 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0. Cycle 3 will be once I start shifting it. Now notice that the seed value just stays on there the whole time, but the only time I care is in that 1 cycle where I'm loading. Okay? So what is the next value? Well, it would be, this one is easier actually because all I have to do now is take bit 7 down to 1, which is those guys, shift them to 1 bit to the right, so I just copy those bits down. All right, is that 7? 1, 2, 3, 4, 5, 6, 7. Yep. And then the new bit I'm going to put in on the left-hand side because it goes there on the left, and it's going to be 5, whatever the old 5 and 2 XORed was. Well, that's 0, 1, 2, 3, 4, 5. So 5 was a 1 and 2 is a 0, so that would be a 1. So I'm going to shift in a 1. Yes?
How do you know if it's just right or left?
It's based on the way you construct this statement. The reason I know it's shifting to the right is because val bit 0 is disappearing. I'm not including val 0 in here anywhere. I'm meaning that it will be lost after this gets evaluated. And likewise, the new value that gets added is being put on the left. So it must be a right shift. I could have done this as a left shift if I wanted to. I could have but if I did as a left shift, it would actually say val 6 down to 0, comma, and then that value. So it would be reversed, but I would lose bit 7 instead of bit 0 from the original value. Any question? Oh, I said use X to specify unknown, so that would actually be, that first one would be an X there. Okay. Basic elements of an FPGA we use in class, doesn't apply this semester. Write a Verilog module that takes a 4-bit value named inval, a 2-bit value named shamped, and outputs a 4-bit value named outval that is the value of inval combinationally shifted left by the amount. Okay, well here's another shift. This actually works out. This is another shift question. So this would just be module. What did I call it? Oh, I didn't give a name. No, I didn't give a name. Okay, foo. Inval. So this would be input logic I say how many bits it was? 4-bit, yeah. So 3:0 in val, comma, and a 2-bit value named champ. So input logic 1 champed, and output logic 3:0 out val. The reason I used out val and in val is because input and output are the reserved words. Verilog. So this one's actually just one line of code, right? I just say assign out val out underscore val equals in val. Now I could just use the shift. Yeah, I'm just going to use the shift operator. Shifted left, right? So left is this way, and then say shamped. Yep, and then end module. That's it. Got a semicolon here on that line and no semicolon on the bottom line. Any questions? Okay, and the second quiz. What are the two types of assignment statements allowed for Verilog code in an always block? How does their behavior differ? Well, this would just be blocking and non-blocking. Blocking takes effect immediately. Non-blocking takes effect after the always statement has been evaluated. List the 3 components found in FPGA. Don't worry about that one. We didn't cover that. Identify any problems with the module below. Okay, well, this is similar to another quiz question I asked you. The problem here is that C is assigned by the assign and inside the always. So an always block is supposed to be like a complicated version of an assign statement, right? You guys with me? So you could, or alternatively, you could think of an always as an assign or assign as an always. But either way, it's like making a circuit. And so you can't assign C in an assign and also assign C in an always, because it'll be double driven. It'll be like having 2 logic gates shorting their output together into one net one wire. Okay, 1 voltage. The other problem is a little bit more subtle. And this is the reason, by the way, why System Verilog introduced always underscore com. It's for this. You have an always at star. This is obviously supposed to be combinational logic. But because the if statement only assigns C if B is true, it doesn't define how it should assign C if B is false. And as a result, the synthesizer will have to generate a latch for this. This will become a latch. Because C will have to retain its old value if B is false. You guys with me? Which means it's a memory. Now you might say, why is a latch? Why is it not an edge triggered? Because this is not edge triggered. This is level sensitive. In fact, it's level sensitive with respect to B. In fact, this is a classical latch. This is a D latch where B is the clock. Right? So the problem, you might say, well, what's the problem with having a latch? The problem with it is that you didn't intend for that to be a latch. Whoever programmed this is a bug. This is a bug because this is what someone would do if they're not used to writing code in Verilog. They're used to regular programming languages. In regular programming languages, you don't have to worry about what happens if you have an if statement that you don't do anything in the if statement because none of the conditions in the if statement were true. You guys with me? So it produces hardware that you didn't intend. It also complicates the timing analysis and probably will result in a slower clock. Think about it. You guys, we did all that work last chapter with the setup and hold time constraints. I don't even know how to do that for a latch. I have no idea. that would be hugely complicated. Like, I don't even know how you do setup and hold time analysis for a latch. Everything we did was for flip-flops. So you want to avoid that. And in system Verilog, if you said always _com instead of this, then then it wouldn't allow you to compile that. So that's the whole reason why they did that, was to prevent that kind of unintentional side effects from happening. I think those are the only problems with that. Okay, any questions? Okay, let's look at, got some time left. Let's take a look at some stuff from the book.
You mentioned 450 specifically.
Yeah, 450 was the one that, it was a similar one where they said, the following system Verilog modules show errors that the authors have seen students make in the laboratory. Explain the error in each module and how to fix it. Yeah, so these are good. Let's see, this one, always at clock. What's the problem? They should have said pause edge clock. If you say this, it becomes a latch. This is a latch.
I mean, since the module's named latch, wouldn't you think they were trying to make a latch?
Oh, yeah, that's true. That's a good point. Well, in that case, is there anything else wrong with it?
The D is inside the clock. Is it in the always statement?
D? Well, if it was a latch, D wouldn't be part of the sensitivity list, because if it's a latch, the purpose of a latch is essentially to ignore D, except for when whatever it's sensitive to is active, right? So in this case, clock is the gatekeeper here. So it's supposed to ignore D, which is why D is not in the sensitivity list there. So that makes sense. Although, that being said, it wouldn't change anything. Even if you had D in the sensitivity list, all that would do is activate the always if D changes, but it wouldn't necessarily change the outcome anyway. So, but if you were trying to create a latch, you would not put D in there, most likely. You see what I'm saying? Yeah. So what I'm saying is it doesn't need to go in there, but if you put it in there, it wouldn't make any difference. I don't know. That's a very good point. I don't know the answer to this one.
Is that A?
Yeah, A. Seems...
Module latch.
Yeah, seems...
It's, look what's inside. Clock D is what it's supposed to be.
If clock...
Like always at clock D.
Okay.
Oh, yeah, sure.
In the always
Yeah.
statement, D should always be included in the statement with clock.
Okay. Well, then you're right then. Good job. So he was right. So according to the authors, they're saying that you should put a D. That's a bad one, because that's a totally unrealistic one anyway. All right, moving along. Number B, or letter B. Module gates, input logic AB, output logic Y1, Y2, Y3, Y4, Y5. Always at A, begin, you set a bunch of stuff. And so we got an always at A. Okay, the problem here is that we left B out. So this is a similar one. Now this one makes sense. This is combinational logic. It's perfectly valid. Blocking assignments, fine. That's what you're supposed to do in combinational logic. Everything is fine. You got the begin and end. This is perfect. But they should have said always at star if they were trying to do combinational logic, or always _com in system Verilog. But because they didn't do that, they should have a complete sensitivity list, which they don't. They just have A. And for this one, it really matters. I don't think it matters on this one, to be honest with you. Oh, you know what? Actually, I take that back. There is a case where it would matter. Now that I think about it, let's say clock is being held high, right? If clock is being held high, then you would want to update Q whenever D changes, right? Because that way the latch would let D through, right? So no, you're right. Actually, and yeah, so that makes sense. I take that back. This should be clock D, and this one should be AB for basically the same reason, right? You want a complete sensitivity list. Okay, now part C, module mux2. I got D. This is a mux. Always at pause edge S. If S is asserted, then I assign Y. This one seems to be, this is a mux, but it's also a registered mux. So this is like, what they're doing here is creating a mux, but instead of having a separate flip-flop on the output of the mux, mux. No, that's an ALU, that's not a mux. Mux is a trapezoid. There we go. Trapezoid, mux, right? They have two inputs, which they call D0, D1, and they have an input select, and they have an output called Y. So that's a regular mux. If you were doing this, that should be combinational logic. They have an always at pause edge clock, which means that they're putting a register at the output of that. The register is being clocked on S. Now see that? But they're also using S as the select for the mux. So is that going to work? Yeah, it would work, except there would be a 2-cycle delay because they're using non-blocking assignment statements here, right? So what would happen is I believe if once S changes its state, it will update Y, but it will be the old, let's see, it will be, well, maybe, let's see, S, it's a good question. To simulate this, to check this out. I would think that if you're doing two things on the output of the S, you're using it as your select, and you're also using it to update the output as well. So when you get a rising edge, you have S, D0, D1, S. So S is going to be rising edge. Oh, sorry. So you have an S, rising edge, and you have Y. Y will update there. But the question is it going to see the updated D0, D1, or is it going to impose another cycle of delay? What does it say? Do you have the solution?
For which one? C?
C.
C, it says always star is what it needs to be.
Okay, well, yeah. If it were just a regular mux, you'd want to do always star. I thought maybe they were trying to add an extra register flip-flop at the output of that. Okay. Well, normally it would just be always star. Yeah.
Yes.
I thought they were trying to deliberately do some kind of delay. Okay. Any questions? Part D, 2 flops, always at pause edge clock. This one is using blocking. It should be non-blocking. Yes, and a begin. That's right. Thank you. Yeah, I didn't notice that one. Begin and end too here. Yeah. Okay. E. Finite state machine. They also forgot. Well, no wait. Is this continue on the next page?
Yeah.
Okay. If this continues on the next page, then yeah. Yeah. Oh no. But it's just another always, though. No, I think we're good. I don't think you need a begin and end for the always.
Oh, I think it was the
right.
Always FF should be used.
Always FF pause edge clock. If state equals 1, then begin. If A state equals 1. So what are they trying to do here? This is the next state logic, right? So the next state logic this is combining the next state and the clocked logic, because they don't have a next state, they just have a current state here. So they're combining the next state and the clock logic into one always flip-flop block. Yeah, I don't know. That's not necessarily a deal breaker. It's confusing to read that. Down here on the next page, this is their output logic. So this is combinational. This is fine. So this seems fine to me. I just think the problem is that they didn't structure. The finite state machine is not structured very well. It's difficult to read. Everyone with me? So make sure you know how to read these FSMs and how to build FSMs in Verilog. You should have a distinct always statement to carry the next state into the current state, right? And then there should be combinational logic that calculates the next state. What these guys are doing is, in this code, they're combining together the clock logic and the next state logic into one block. Yes?
So whenever it says if A then state equals 1,
Yeah.
for that, are they saying that if A is 1?
Yes, that's right. Yeah, so if they're in state 0, so they have a state, they just have two states, 0 and 1. And if you're in 0 and A is a 1, you go to state 1. If state is not 0, then state must be 1, right? So this else is for state 1. And if A is 0, you go back to state 0. Right? If you're in state 0 and you get a 0, then you would stay in there. Likewise, if you're in 1 and you get a 1, you'd stay in there. Right? So that's the state machine this is creating. It's kind of redundant because it's just creating a flip-flop, essentially. 1-bit flip-flop. Okay. B. This one is the way what I described earlier. They have an if statement, but they need like a catch-all, a default output, because if you don't, depending on how you go, like for example, if A was all zeros, 0, 0, 0, 0, none of these ifs would be evaluated, right? So there's no default output for that guy. So that would create well, actually you'd get an error because it's defined as always comb. This is a divide by 3. This parameter, by the way, I think I might have mentioned this in class. In Verilog, the way that you would define states is through parameters, and you'd have to assign values to them manually. They didn't have enumerated types in System Verilog. But that's not a big deal. They're just creating 3 states. They have a state and a next state. The state register says always a flip-flop, always underscore flip-flop, pause edge, clock, pause edge, reset. If reset, you go back to state 0. Otherwise, next state is a state gets next state. Your next state logic says always at state. That's problematic, right? That should be always at star. Although I guess it doesn't matter because there's no other inputs besides state. So that's actually okay. Still, I would put always at star, but this is actually acceptable because there's only one input to this case statement. And assign out state equals S2. That looks fine too. So this is a divide by 3 counter. This is very similar to the one that we looked at from the book. I don't see a problem with this one either. I must not be seeing it.
I just put it up.
This one is very subtle.
If I'm correct, it's saying that the next state is a default statement.
Oh, yes, thank you. Yeah. I didn't catch that because they covered every possibility in this case. So having a default is actually redundant, but the compiler might still give you an error or it may get confused because there's no default, right? So you have to be careful with case statements. The book actually says, if you go to the book lecture slides, under the case slide that I presented, it actually says that you're supposed to always have a default statement for a case, and they don't have that here. Okay, great. How much time do I have left here? Almost out. Okay, okay, so the rest of these are just 2. If you have any questions about the rest of these, let me know. Send me an email. Make sure that you understand how to build those state machines in Verilog. How to like if I give you a state diagram, you should be able to write the Verilog for it. Or if I give you the Verilog, you should be able to go backwards and generate the state diagram from the Verilog, right? So for example, in this one, if I were going to do it for this one, basically what you do is you create a state. You know that there's 3 states, S0, S1, S2. So you start with your states. And then these next states, you know, S0 goes to S1 unconditionally, S1 goes to S2, and then S2 goes back to S0. Right? Now in this case, this logic does not care about the input. These are all unconditional transitions, so I don't have to put anything on these transitions. They're just empty. Right? And then this is my reset state here, S0. Right? So you should be able to take this code and go to a state diagram. Right? Make sure you can do that. And make sure you understand test benches and how to write a self-checking test bench, like we did a few minutes ago. Okay? And make sure you remember that, you know, if you have combinational logic, you have to assign all outputs every time the always is evaluated. And then, you know, from there, it's just kind of the basic syntax of Verilog. I can't think of anything else in particular.